對我嚟講冇所謂，最公平嘅。I think it's fair. Open book, close book, I don't care. So the problem is whether some of people are cheating with each other, which I can't observe. But if everyone can cheat, it's fine. But the problem is someone cheats, someone didn't cheat, and it's a problem. So I need to be very careful. So let's get started. So I think we covered the first 1/3 of this one, and I think on Wednesday we'll cover it, but I don't think we can we may not be able to finish all the lab things. So it is possible that we will have to do it Monday again on the lab. So it depends on how we progress, but I'm not entirely sure how it goes, but let's see if we can finish it. Try to be as fast as I can, but cannot be confirmed. So what are we going to do? I think last time we covered the Z test, right? Am I right? We cover the Z test, right? So today we will cover, probably you forget, right? But anyway, we will cover the T test and top of portion. Basically, we'll finish the one sample test and try to touch something on the 2 sample one. Okay. And just to remind you that what we are doing for the hypothesis testing is, for our purpose, is want to see if the population mean is equal to a certain number. And why we need to do that, there are many applications, right? This is what the data people use for, right? It's the data to validate certain of claim, right? For example, you want to check if certain harmful substance in the food is above the legal requirement, or the active ingredient within certain health product, is it above what it claims, right? Or you are quality controller, you want to make sure that the content is no more or no less than the required desired accuracy. So this is all the applications. Okay. So this is the 1 sample test. If we have time, we talk about 2 samples, but because just 1 sample, just look at the population and look at the mean. Okay. So so this is the idea we call the null hypothesis, the alternative hypothesis. Oh, if I share the screen, I think I've not yet shared the screen yet. So and the logic of hypothesis testing is you have some hypothesis about the population mean. You are trying to look at data and see the data support the claim. Okay. If it is too far away from what you propose, then you reject. Okay. And how to determine far away is in terms of probability, the area under the curve. And then if it is too low, then you reject, right? So the null is, for purpose, is always simple. The composite is always related to alternative hypothesis. Okay. So just to remind you, 1-sided and 2-sided, when you use which, you determine application. Okay. Either the questions tell you or you have to infer by yourself. Okay. Just to remind you that when you use which is depend on when you will consider rejection or null. Okay. For example, you want to see whether there's a harmful, more than certain level of harmful substance, we consider as a violation of the law and regulation. In that case, the alternative hypothesis must be more than, because less than certain level doesn't consider a harm. Okay. So that will really depends on which one you pick on. Or you have some prior knowledge about what you want, then you will be you will decide 1-sided or 2-sided. Okay. And indeed, in your mind, actually the alternative hypothesis is something you want to prove, right? The null is something you actually want to reject. Okay. or the null is something is a working hypothesis. Okay, so just to remind you the type 1 error and type 2 error, regardless of what you do, okay, even though it's away from hypothesis testing, whatever statistic decision you make is always involved 2 error. One is type 1 error, one is type 2 error. Type 1 error is given the null is correct, okay, you still make the wrong decision because of sampling error, okay. And type 2 error is the null is wrong, but you do not reject, okay. And do note that in our purpose, alpha is decided by us, okay, and beta, which is difficult to calculate, okay, it's difficult to calculate, but it can be shown that for best procedure, okay, increase in alpha will reduce in beta, and reduce alpha will increase beta, okay. They are moving in opposite direction, okay. That means that if you there's no free lunch, so if you want to reduce both, you need to increase your sample size, okay. The more sample you have, you can reduce both, right? So that is the underlying idea, okay. And just to remind you again, the rule of thumb for alpha, okay, which you have control, beta we don't have control, just remember. But alpha with direct control, we can put 1%, 5%, and 10%, okay. And why someone asked why I don't have 8% or 7%, but just meta convention, okay. So you can definitely use your own, but we all use this standard 3 different levels of alphas, okay. And this is the way how you can do the hypothesis testing. First, you can tell the people what the H now H1, okay, and then you create a test statistic based on the assumption, okay, and then you either compare the test statistics to the critical value, okay, or you calculate the p-value and compare with alpha, okay. So one or the other is fine. Okay. So the key here, one thing is one sample for the mean is whether you know the variance. If the variance will be z, okay, which we are going to review, and then we're going to talk t, okay. And so yes, so the null hypothesis. So we just do the first one, do the right tail, or we let's quickly review. Okay, maybe we just go to the example. I think that's quick enough. Okay, put the example directly. So this example says the following. Okay, so you know the standard deviation is 4, and you have random variable sample mean, and it's 64. Sample mean is 5. So just let me quickly go over that again. Hopefully that will be try to be fast. Okay. So this is the screen is very slow. So the normal with mean, sorry, I just used the whiteboard because I think the screen is super slow. So basically it's this, right? So this is under the null, okay? This is 4 here, okay? And we know n is 64 and sigma is 4 here, okay? So what we know is we try to convert it to the z space, right? And this is going to be 0, right? And how you convert this is 6 bar minus mu, which is 4 over sigma over root n, right? So what the data tell us is what we have is the data is the sample mean is 5, okay? So one obvious question is again is we check the data, is it favor the H1 rather than H0, right? We say if it is too big, right? Then we will say the H null will be rejected. So this is the hypothesis, right? So for too big means this is area is it too small or too big, right? Then actually this is called p-value, right? And if this value less than alpha, then we say it's too far away, right? And we do the same procedure to convert this to here, which is 2, right? Because 5 minus 4 over 4 over A, okay? So this area, okay, turn out to be, how to find this area, just remind again, this is 1 minus norm as this 2 true, okay? If you are in Excel, that if you out, then you just P norm or D norm, anyway, just forget, just do the Excel first, okay? This is the answer, okay, and give you this number. And another way to do it is look at the critical value, right? And look at this number, how to get 5%, right? Which is set alpha, right? If you want this to be alpha. And look at the answer here will be 1.64, okay? So that's why when your test statistic is beyond the critical value, then you reject, okay? Regardless of you use which way. Actually, the data, what the data show is your sample mean based on the null hypothesis is far away, okay? So that's why you reject at the alpha percent significance level, okay? I hope that is clear because I think we have run this many times. May run this again for the left tail test. I just run this again here in case you would want to see again. So this is by the central limit theorem. Okay. When the sample size is large enough, okay, the sample mean looks like normal, looks like the normal, right? And approximately look like this, right? 4 sigma is 4, right? And it's 64, okay? Do note that is the central limit theorem said it is approximate, right? So actually, central limit claim this directly, right? It's actually norm. Okay? So actually, the central limit theorem claim this directly, right? This is what. Okay. This is what the central limit theorem said. And now, what the data tells you is the sample mean is 3. So it's here. Okay. And remember, you reject the left, okay, because there was a question is given to you. So the question is asking, like whether this area, according to our definition, the test is asking this area, actually called the p-value, is smaller or bigger than alpha, which is the type 1 error decided by us. Okay, or significance level, we use the 5% as normal. So asking whether the p-value is less than or more than 5%. Okay, so basically you convert this here, the 3, according to this formula, it's just -2. Okay, and just the same as there, just symmetric case, this area, okay, is 0.022A, okay, which is less than 5%. So you would reject at the 5% level. Of course, if you use 1%, okay, then you cannot reject. Okay, so if you 1%, you do not reject. But if 5%, you reject. Just make sure that you understand this with the alpha. Okay, if 1%, you don't reject. And the other way around is look at the critical value. As we have seen it, the critical value is negative 1.64, right? For this to be 5% alpha, right? This is C alpha negative. So that's why we reject. Okay, so just to make sure that this is clear. Okay, so just to remind you that if you use 1%, then you do not reject. Is that okay? I think we covered this last time, so I don't want to spend too much time on this one. So let us finally go to this two-tailed test again. Okay, for two-tailed test, it's slightly different. Okay, in terms of p-value and the area. Okay, so here just do the example again directly. So maybe I can use the whiteboard again. If I try to use this whiteboard, hopefully your fellow classmate from the Zoom can see it as well. So what we'll be showing is this question again. Right. So this one looks like this. Under the null, this is 4 here. Okay. So we would say that this hypothesis will be rejected if it is too far away from 4, below, above, right? So that means that if this is too small, okay, on either side, that would be rejected, right? So we want, when we say alpha, we want the middle to be 1 minus alpha, right? So the both side is alpha over 2. Okay. If your data is within the blue region, which sometimes we call rejection region, then you reject. Okay. So the question is whether the data you figure is 3 is actually in this region or outside this region. Okay. So the data you have is 3. Okay. Sigma is 4 and is 64. Okay. So just to remind you that this is normal, so that's why this is also the normal. This should be 0. Okay. So to convert 3 from here to here, just follow this formula, right? So what we have is actually -2. Okay. The question will be, is this area, okay, is this area, because we cut alpha over 2, is this area less than or more than alpha over 2? Okay. So if you want to keep the original idea, you can say this value times 2 is better than alpha or smaller than, right? So that's why we said with this times 2 is the p-value. Okay. Then we can compare this value with alpha. Okay. So same as there, the area of this area is 0.0228. Okay. And multiplied by 2 will be equal to 0.001. 0.0456. Okay, so luckily this is still less than 5%. Okay, if you use 5%, okay, then you will still reject. Okay, of course you use 1%, you don't, right? 10% also you do. Okay, so so that is the idea. Okay, the p-value is a little bit different. Okay, for critical value, it will not be different, right? Because critical value, what's the critical value here, right? This area, right, will be z alpha over 2, negative z alpha 2, right? So this, right, just is 1.96, negative 1.96. Okay, so it is negative 2 is still more extreme than the critical values, so you would reject at 5%. Okay, don't worry, we'll be doing the same procedure exactly now as we do t-test. Okay, when we don't know sigma, okay, we replace everything by t. Okay, replace z by t of degree of n-1. So we'll repeat the same procedure. Okay, so don't worry. So let us tell you the t-test. Okay, so the t-test is saying that the same thing, but now you do not know the sigma, but you know, then you have to calculate s squared. Okay, then you would follow this, right? Because this is exactly what we learned from the estimation, right? If you don't know this, we have to use this. And student, okay, I mean, he proved this is the case. Okay, so basically, if you still recall, this, right? For the confidence interval, right? If you know the sigma, this is the case. Right? And if you don't know, this is the case. Okay? So exactly that actually follow from this one. Okay? So basically what we do is exactly follow what we should do, but replace everything by that. Okay? So let us go to the exercise. Okay, so let's do it together and you will see how we get it right. Okay, so let's do it slowly on here. Okay, so loosely speaking, this is what is happening, right? This looks really much like Bell, but not exactly Bell. If you are just using the sigma, okay, you know sigma, then it's more like normal, but you don't know, you have to estimate S. So it looks like a little bit more clumsy stuff. Okay, so what you want is, okay, under the null, okay, this is 4. Okay, and the shape can be not exactly Bell, but you can still a symmetric thing. Okay, now under the what we learned, right? So if you consider T, okay, which is x bar minus mu over S over root n. Okay, and this guy looks like a T distribution. It's like a bell, but it's like both sides higher. Okay, it's still a 0 here. Okay, so it's T distribution. Okay, indeed it depends on how many samples you have, right? This is indeed follow the T Tn minus 1. Okay. Okay, so this Tn minus 1. Okay. So the only difference is here when you replace S become instead of Z is Tn minus 1. Okay. So the question again, the one-tailed test, all right? So one-tailed test imply you're looking at the right-hand side, right? Right-tailed test, right? If it's too big, okay? The question is it too big or too small? If it's too small, then you reject, right? So the answer is here is 5 here. This is data. Okay. The question is you convert this 5 into here. Okay. Is this area too big or too small? Okay. And how to convert from the above to below? You minus the mean over S over root n. So this is this formula. Okay. So 5 minus 4 is 1. 2 over root 4 is root 16 is 4. So 1/2. So it's 2. Okay. So that's why this is 2 here. Oh. Okay. 2 is here. Okay. So now the question is 2 is in terms of T distribution with n minus 1. So we need to check this one out. Okay. So this is, if you still recall the way we do in the previous class, this area will be just the left hand side is just T this. So the right hand side will be 1 minus T. So we have to go to right here. T dot this, okay, 2, and then 63, and then true. Oh, that is very difficult to write. Okay, so it's T this 2, 63 come from n minus 1, and true will give you this area. Oh, sorry, not 63, sorry. Now the sample size is 15, right? So it's 16 is 15. Okay, so we can show you the Excel. Let me open the Excel to show you that this will give you the last area 0.3. Okay, so let me open Excel. One minus T this 2, 15. Okay, so this is going to be the number that we want to do. Okay, so if we use alpha is 5%, then this p-value is smaller than 5%. You reject the null at 5%. Okay, but if alpha is 1%, okay, then you would not reject because the p-value is bigger than alpha. Okay, is that clear? Okay, now the next thing I want to say is you may want to calculate the critical value. Okay, this is the p-value method, but critical value, how can we do that? Okay, the same idea here. Okay, we look at what we do is look at the 5% tail. Okay, so let me use the orange color, right? So we want to have this area is 5%. Okay, so this is just T inverse, right? And then if 5% on the right hand side, the left hand side is 0.95. Really cannot. Okay. It's too bad. How can I write it properly? Okay, so you have to input the area on the left and also degree of freedom. Okay, so let me do the Excel. So it's T dot inverse. Okay, for 95 degrees and 15. Okay, so which means that this area on the 5% will be 1.73. Okay, so which is less than 2, or 2 is more than the critical value, you reject. Okay, so exactly the same procedure. I hope by now it should not be an issue for you. Is that okay? I know it's rather repetitive, but sometimes you need to repeat enough time for you to see the same procedure. Is that okay? Of course, we are not going to repeat all the time for the rest of our class, but after this left tail, we will do another left tail. Then every time we will do two tail. Okay, we're not going to repeat everything every time because it's too boring. Okay, this is the last time we do the right tail, and then the next one we'll do once more the left tail, and for the rest of the slides we only do two tail. Okay, the left tail and right tail you should able to follow the same procedure. Okay, I'm not going to repeat ourselves too many times. Okay, is that okay? Any question? Okay, so let us do the very last time the left tail, and then we're not doing the left tail or right tail. Okay, we'll just do two tail. So that's exactly the graph I have here. Okay, so the same procedure for the left tail. Okay, I'm not going to go over with you every single slide, but I want to do the exercise again. Okay, repeat it. Okay, and see if you can follow me. Okay, or you can do it in your mind or in your note. You should be able to do it. Okay, this last time we do one tail. From now on we'll do two tail. So the question is this X bar. Okay, it looks like this under the null hypothesis. This is 4 here. Just to remind you that, I mean, when you have the alternative is less than 4, that means that if the data is going, the sample mean give you is way less than 4, you reject. Okay. So turn out to be your data, what the data has is 3. So the question again is asking you to check if this area is less than our desired significance level, which we use 5. Okay, and as I said in the exam or in the assignment, you'll be given what's the significance level. Okay, but in your project, you expect to do 3 of them. Okay, of course, if you reject at 1%, it implies 5%, 10% as well. Okay, but you only reject in 5, but you may not reject in 1. Okay, so that is certain thing you want to keep in your mind. Okay, now what we want to do is to check the red area is less than or more than 5% compared to the p, that is the p-value, right? So this one is not really normal, so that's why, or because we don't know the sigma, and we have to estimate the s, and then we have to convert to t. Okay, because only this, after the conversion, this become a t. Okay, and which depends on the sample size is T15 here. Okay, because we have a sample of 16. Okay, and we can draw a bell, similar to bell shape. Okay, it's still a mean 0, right? Remember T difference is the mean 0. Okay, it's not a symmetric, it's a symmetric one. Okay, but you have a skewness is 0, but kurtosis is more than 3. Okay, Mean is 0. Variance is somewhat complicated to say, but we know this is the following. So we need to say what is 3 converted to here, okay? And using the formula here, right? It's minus 4 over 2 over root 16 is negative 2. So the same idea, this negative 2 is over here, okay? So we want to know the p-value, right? This area, okay? So it's very simple, right? This one negative 2, so how to convert it is just t this negative 2 and then degree freedom is 15 and equal true. Okay, so t this negative 2, 15 true. Negative 2 is given by here, 15 is degree of freedom, true is because of the area on the left, right? So t this is the area on the left. Okay, so give you this area. Okay, I'm not going to do the Excel. Okay. So the next question is this critical value method, right? What is this area if it is 5%, right? The next question is another method. You don't need to do the both, you just need to do one. But in case you want to do the critical value method, want to calculate this area, okay? This area, right, is T15, okay? 5%, but it's negative, right? It's on the at this side, you flip it, okay? It's negative 1.735, okay? Or you can do the Excel input, right? Because the left-hand side is 5%, you can just do T inward 5%, hey, 0.05 equals to 15. Okay, maybe I show it to you for this one. Very annoying. So this will be just T dot inward because the left hand side 5%, so it's 5%. And degree of freedom is 15. Okay. So this is exactly what we want, right? Because negative 1.7 is here, negative 2 is here. Negative 2 is beyond the critical value. So you do not, you reject it at 5%. Okay. So I guess I'm not going to talk more about details here. So this is last time we do one tail. Okay. From now on, everything we do is two tail. I assume one tail for you, you can handle it. Okay. I'm not going to repeat myself every time I do a two tail. Okay. So let me do a one more time to do two tail for the T. Okay. Is that okay here? Okay. Because I'm not going, it will be very boring if you keep doing all this again, over again. Okay. So let's finally do a one more time we do two tail test. Okay. These two tail tests, do remember that the p-value will be a little bit different, right? The p-value will be the tail area times 2. Okay. If you want to find the critical value, will be the two tail area is alpha over 2. Okay. So that will be a little bit more difficult to see. But later I will try to show you that there's a close relationship between confidence interval and two-sided hypothesis testing. Okay. But later you will see this is related closely with the two-tail test. Okay. But let me finish this before I talk about those. Okay. So what I want to do is to do this again. Okay. You will see exactly the same as what we have seen. But let's quickly finish this. Okay. So again, we have this guy, right? The X bar. have the mean according to the null hypothesis is 4, okay? So do note that this is different from the one-tail test, right? Unless your sample mean is exactly 4, you need to do all the way down, okay? If you just do one tail, okay? If you figure out it's right, suppose right tail test. If your data is less than 4, then you don't need to go, you don't need to do anything, right? If you do a left tail test, right? If your data is more than 4, you don't need to do anything, right? Because for sure you don't have any rejection, right? But now when you have a two-tail test, okay, unless you get exactly 4, okay, or so close to 4 that you really don't do it, but otherwise you have to do it, right? Because it's possible to reject on both sides, okay? Why? Because you are saying that we're going to saying that if this in this are the rejection region, right? And how big are the rejection region is alpha over 2, okay? These two area the rejection region, right? And for this one, X bar is difficult to see, right? But it's not what distribution looks like, a little bit difficult to say. But we know that by the proof we have is use the black color here. This is T15. Why 15? Because it's n-1, okay? And this one we have mean 0, okay? And look again, okay? Our data set is 3, okay? So somewhere here, okay? So we want to convert 3 downward, okay? How to convert it downward? Because from this to here require this formula, right? What you found minus the mean 4 over S over root n. This guy is -2. Okay, I hope with so many exercise, this shouldn't be an issue. Okay, -2. And so the first thing to do is maybe we can do p-value first, okay? Because it's easy to see how to do the p-value. Do note that the p-value we have to multiply the area by 2. Okay, multiply the area by 2. Okay. So the question is, this area is you calculate area to the left or to the right? Because here we have the two things. The rule of thumb is you just calculate the area closest. Okay. If you're on the left hand side, okay, calculate area to the left. Your right hand side area to the right. Okay, and I'm times 2. Okay. So because -2 is on the left hand side, so we calculate area to the left. Okay. So we calculate the tail area. Okay. And this area, right, would be just very simple. Would be just T this -2 15 okay true. Why it's not writing? Okay. And remember, this is not the p-value yet. You need to multiply by 2. Okay. So for Excel, you need to have 2 times this guy. Okay. So let me show in Excel. 2 times T this -2 15 true. Okay. So this is how you arrive the answer there. Okay. So you can see it. Okay. One side is 0.3 something because multiply 2. One side is 0.3 something, and you multiply 2 is 0.6, which is more than alpha. Okay. When more than 5%, then you will say, oh, we can't reject. Okay. If you use 10%, you still can say, uh-oh, we still reject. Okay. But if 5%, say, no, I mean, it's okay. We still keep our hypothesis is equal to 4. Okay. Of course, if 1%, then of course you can't. Right? Because way more than 1%. Okay. So you only reject this at 10%, but you can't reject at 5 or 1. Okay. So that is the idea here. Now, another thing is before the break, what is the critical value? Okay, or the critical value method, right? We want to find the blue thing. What is the rejection area? What's alpha 2, right? So because they're symmetric, right? So just calculate the right, either the left or the right we find. Okay, so this one, right? This is just T 15. Suppose we use 5%, then we will just 2.5%. 0.0025. Okay. Okay. So look at this value and you flip the other side, and this will be the true rejection region. Right? And how to find this is just if you want to find this, right? In Excel will be 0.975 because the right hand side is 0.25, the left hand side is 0.275. Okay. So this in Excel will be just T inward sorry for the writing, but it's because the pen I cannot really, the pen is not really responsive on this screen. So I can just T inward 0.975 15. Okay. So let me show it the last equation, then we can have a break. T inverse 0.975 15. Okay. So this means that is -2 is inside here, so it's here, right? Oh. So it's, what am I doing? So, oh, where's the thing? It's gone. But anyway, we have -2, but it's -2.3, so it's like less than this is way this critical value is -2.1, and your calculated value test is 2, so it's not further than that, so you can't reject. Okay, so I guess we should break. Okay, let's resume at 10:30. Okay, let's have a break. 做你返屋企先啦。So, let's get started. Okay. So before we proceed to the next part, I want to explain how the two-sided test related to the confidence interval. Okay. So they are really closely related. Okay. So remember what we learned by this is a little bit advanced. If you get it, it's okay. You don't get it, it's also fine. You can just remember the conclusion would be okay. Okay. So what's the conclusion? I want to stay here is, okay, let's consider, we know the sigma. Okay. So consider this one first. Okay. The same will be said for the t. Okay. So if we do the two-sided test, it's like this, right? H now is mu equal to A. H1 is mu not equal to A. Okay. So how do we construct this? Right? The construction is saying this plus minus this guy. Right? And how do we construct the T statistic? Right? Is X bar minus A over sigma over root n equal to the test Z. Right? Look at here. Okay. And what at the end, okay, we will be comparing this is, look at this, we compare this is whether this Z is more than this or Z is less than this, right? Because the two-tail test, A is here, right? This is Z alpha over 2, and this negative Z alpha 2. Okay. If in these two areas, then you reject. Right? In this two-tail area, you reject. Okay. So it's reject if this is bigger than, so what is your rejection, right? Your rejection if this guy is bigger than this or less than this, right? So the asking is this guy. Okay. If you'll be rejecting if this guy is bigger than C alpha over 2, or this is less than Z alpha 2. Okay. So if you just try to rewrite this too, okay, what you have, write this too. Okay. The first one become the following: X bar minus C alpha over 2 bigger than A. Can you see that? Multiply this. Maybe I write it here. Okay, am I right? So look at this expression. Okay, look at the first expression. Okay, can be written as X bar minus is that okay? The first one, the first equation is equal to this one, right? The second one is X bar plus right? Okay, So what does that mean? You'll reject if this thing happen. Okay, this is the UCL, this is the LCL, right? So if your LCL is less than A, you reject. Okay, so just to remind you what you're doing, this is your X bar, right? You go left by ME, right? This is the UCL, this is the LCL, right? So if your A is outside, is beyond, right? If A is here, like this. If A is here, if such like this, is A is here. Okay, which means that if what you hypothesize, okay, is outside your region, then you reject. Okay, so let me repeat the statement. Here is, suppose you have the data, you construct the confidence interval. Okay, if the interval doesn't include the A, right, then you will reject. Okay, to further understand this, you look at this graph. What we are doing is the A here, right? We have X bar here, say. Okay, and here we actually can construct the ME. Okay, here I can do the same, do the estimation, right? If this, in this case, this is the interval estimate. Okay, if the interval doesn't include A, you reject, right? If you include, you cannot reject, right? The reason is very simple, right? Because if included, you cannot exclude the idea that there's actually within the range. Right? Let me repeat the statement, right? If you do the confidence interval, you include the null hypothesis, right? That it actually means that this is within your estimation range. So you really cannot reject. Okay, of course, this is a little bit advanced here. I'm not expecting you to replicate or what, but I hope this is making kind of sense. Okay, how is closely related between hypothesis testing and interval estimate. Okay, actually we will use this concept to, when we talk about two sample tests, we just assume this is the case. Okay, we're not going to repeat the idea. Okay, so just to repeat again. Okay, there's a close relation between hypothesis testing and interval estimate. Okay, and if you do interval estimate, okay, if you collect the interval, okay, and the interval will include this the null hypothesis, okay, then you cannot reject. Okay, so of course they're closely related. At some time there have to be the margin of error has slightly different. There will be some slight difference. Okay, but I think for our purpose, later you will see. Okay, when I have sample mean, population mean, they're identical. Okay, and when we go to the next slide, the proportion, they'll be slightly different. Okay, but because of the margin of error, okay, how we estimate margin of error is slightly different, because under the null, this is a little bit different from when you do estimation. Okay, but anyway, is that okay? Now, what I want to continue is something rather simple. Okay, it's the following. So remember, when you do proportion, okay, with the following, right? I hope I can erase. So for proportion, we have the following confidence interval, right? P plus minus CR/2 we use P, right? Okay. This is the interval estimate for proportion, right? So the difference between the interval estimate and hypothesis is here, okay? Because under the null, okay, we know the mean is pi, okay, and we do not use p here. We can use pi directly. Okay. So that means that the z-test will be p minus, later you will see the slide, will be p minus a over this guy. Okay. The should be a. Okay. So that is it's not p minus p. Okay. So that's the only difference here. But I will let you see the example here. Okay. So under the null, okay, I just do two-sided. One-sided will be same thing. Okay. So we just say the proportion is equal to what? Okay. So just to remind you why you want to do that. Okay. So suppose I think this is something people often ask, okay, is whether we are do away with the nuclear power. Often happen in Japan or Taiwan or Europe. People want to do away with nuclear power. Okay. And you want to see how many people want to do away with that, right? So it's the same proportion, right? And according to law of large number, or sorry, central limit theorem, when n is large enough, this minus a what you propose over this a minus 1 a, this guy's normal. Okay, so that's is here. Okay. So again, if two-sided, everything the same thing, just no difference. Only except the thing is, we really need not know sigma. Okay. The reason is the sigma and that's s. You really need to do it because under the null, the variance is given by. If I say now the population proportion is pi, already the variance you know. Okay. There's no idea of known variance or unknown variance. Okay. Because when you make the hypothesis is a, proportion is a, it's a fraction. Already, you already make also the assumption on the variance already. Okay, because proportion is only a one number thing. Okay. So let's see the example. So I think the example would help you to see all the calculations. Okay. So here we have n is 50, sample proportion is 0.5, okay, and pi is 0.4, okay. So what here we do is we claim the fraction, the population fraction is 40%, okay. You can measure maybe 40% people like Mura, okay. And you figure out that, okay, more than half of people, exactly half people like Mura. You know what's Mura? You know what's Mura? Yeah, you know, okay, good. And that is the idea. Okay, so remember this is normal. So this, okay, supposed to be a bell shape. And under the null, this is 0.4. Okay, it's a two-tail test. Okay, so that's why it's too big or too small, then you reject. Okay, so what the data tells you is actually it's 0.5. Okay. The question is this area is too large? Okay, then you reject. Remember, you're doing two-tail test. Okay, so you put one alpha over 2 on both sides. So suppose 5%, 2.5 on each. So the question is asking whether the alpha is more or less than 2.5%. Okay, or 2 times this area is more than 5 or less than 5. Okay, let's go the easier way, multiply by 2, right? Multiply this 2, is it more than 2 and less than 2? right? And we know that we can just simply convert it to the, again, go to the Z, right? This will be 0. And what is 0.5? Okay. This 0.5 is based on this formula, right? Minus the mean over this interesting guy, right? Here. Or same as what you see in the, okay? Do note that the difference, okay? When you do estimation and hypothesis testing. Hypothesis testing, okay? You use the what you hypothesize, okay? But for confidence interval, you use what you want to put in. So they're slightly different. Okay, they're slightly different there. Okay, so not in this case, when we do hypothesis testing and interval estimate, you can have different idea, right? You can have different conclusion whether 0.4 is within the interval or not. So again, the rejection are slightly different. Okay, so that's why we need to learn two things, right? Otherwise, we can just end just like why don't we just estimate the interval and then further see whether inside or not. Okay, that's a slightly different here because we put extra assumption on hypothesis testing. We make some extra assumption, but interval estimate we don't make an extra assumption there. Okay. So here, when you convert it, it's 0.144. Okay. So as again, we want to check this area multiplied by 2. Is it multiplied by 2? Is it too, sorry, is it too big or too small? So, sorry, this is 1.44. Sorry. Is it bigger than, multiply this by 2? Is it bigger than 5% or less than 5%, right? And how to do it is this area 1 minus, right? So this is just like 1 minus norm this 1.44. True. I will just write down in case you don't follow, right? Because the area you have Excel on the left, so you need to 1 minus norm this 1.44 true. Remember, you need to multiply by 2. Okay. So you have to 1.44 true, 1 minus because of left hand side, and you p-value is multiplied by 2. Okay. Just remember why 1 minus, because Excel gives you error on the left. You want the right area is 1 minus. And why multiply by 2? Because you are doing two tail. Okay. Two tail always multiply by 2 because you only compare 5%. If you don't want to multiply by 2, you just compare 2.5. But as a standard, the p-value is 2 times the tail area. Okay. So turn out that I think I'm okay not to repeat this in the Excel. This is number. Okay. So that means that you reject 5%. If you do 1%, also reject, of course, because we reject. You cannot reject at 5. You can't reject at 1. And turn out this also you can't reject at 10. So regardless of use 10, 5 of 1, you can't reject, right? Because this is 14%. Okay. So basically, you can see in this question, right? Proportion is not easy to reject, right? Even though what I say is 0.4, right? You get 0.5, you only get sample 50, then it's still a big number. Okay. So that's why for proportion data, you need to do a lot. Okay. So that's why probably you have to do several hundred to reject this. Okay. Usually N is for proportion, if you just ask 100 people, usually you cannot do too much thing. Okay. So that's why when we do survey, at least 1,000. Probably I mentioned it last time already. The sample size estimation, sample size determination of sample size. When you do when you try to do the accuracy, right, for the sample size. For proportion, at least you reach several hundred to be useful. Otherwise, even you can see this, you can reject. You can't reject. Okay. So you can also do the, this is done, right? But also you can do the other way around, do the test statistic, right? Look at the both n 2.5%, whether you reject or not. Okay. And we know that's 1.96. Okay. And it is far beyond here. Okay, so we reject. Okay. So in the break, someone asked me, probably I didn't answer, I didn't spell a lot, is why we need to use two methods. Okay. Why don't just p-value is done? Okay. The reason is historical. P-value, now your calculator is so fast you can do it now. Okay. But without calculator, p-value is very difficult to calculate. Okay. But this value, the critical value, is always fixed. You can see the critical value is independent of what the data you have. No matter what data you have, it's always 1.96. No matter what is the p, what is the n, it's already fixed. Okay. But this one, you have to know all different kind of value. Okay. Which is somewhat difficult to do. Okay. When you don't have computer. So in the old days, look at the probability textbook, which is like 20 years ago or 10 years ago. This method is still the most useful one. Okay, but now the computer, even your iPhone or even your smartphone, can do it less than 1 second. Okay, so that's why this one actually is not really that attractive. You can just do that. Okay, but in order for you to read the textbook, I just introduced two. Okay, I think 10 years from now, I guess we don't need to teach this one. Okay, we just need this one because the same thing, right? Looking at how extreme the number is, right? So the same thing. Okay, is that okay? Cool. Now that is good. Any more questions? Because we're going to do the two sample one. Is there any question? By the way, did I talk about the project in the class last time? Yeah. Okay, and that's good. I don't need to repeat. So now if there's no question, we talk about two samples. Okay. So far we talk about one sample, and then we're trying to see the sample mean equal to some number, or the sample proportion equal to some number. Okay. It do have application we have mentioned a lot. Okay. But the question is sometimes is how the number goes in, right? Why the sample mean equal to certain number. Okay. And of course that is actually come from your estimation, earliest estimation, right? Before you've estimated what is how you get the the machine, right, comes out bed of rice is 5 kg, right? So how can you come up with that? Historically, you measure the thing, right? The machine tells you this is the number you want to test it. Okay, so a lot of application, but sometimes that you really the application is you need two samples. You're comparing two samples, whether they're same mean or different mean. Comparing is a lot of time you use it. Say for example, a lot of time people want to know whether people taking the Sinovac or the BioNTech, do they have the same antibody or not? Right. Another question would be, is people taking two vaccine better than one vaccine? Okay. Is it taking 3 vaccine better than 2 vaccine? Is it 4 better than 3? Is it 5 better than 4? So on and so forth, right? So we want to see how is it more vaccines better, right? Sometimes may not be, right? Because right, so that maybe because you bring more, maybe just basically no change, right? It can be, right? Or taking too many vaccine, then basically people die. Okay, can be, right? Because if suppose you push 1,000 vaccine, probably I bet that guy will die at the same time. So that have to be some limit, right? I mean, you know, like even drinking water, okay, if you drink 1,000 water, I mean, you will die. Okay, I think you drink more than 10 glass of water, then you just die. If you can take 10 glass of water at one time, right? But anyway, So comparison is very important. Okay, just like when you want to also, as a marketing or advertising or managing, right? You want to see whether marketing manager say, I put a booth, advertising booth in the subway station, right? How is the sales over there? Or also compare, I put the booth in, say, in the canteen. Okay, which one is better, right? And then you compare, look at the data, and then you can compare which one gives you more revenue, right? So on and so forth. Right? There's a comparison that a lot of times you want to compare as a manager, you want to compare, right? So that would be the case, or you are auditor, right? Try to check the inventory or the sales condition for one particular store, right? And probably you don't know what is the hypothesis there, right? And what you want to do is a internal control. You want to compare similar stores, right? You want to try to see if actually they are doing similarly. Right? Suppose they should be similarly, right? If you open 2 stores in 2 similar locations, you should expect 2 stores would behave similarly, right? If one store is all the time doing very bad, either the manager is not doing the right job or there's something goes on there. Okay, so this is 2 samples is very common. Okay, so so there are 2 things I want to compare. Is compare means. That is the first one we do. Okay, the second one is compare variance. Compare variance is somewhat useful. Is whether compare say quality control, compare 2 machines, do they have the same accuracy? Okay, or if you think about return, stock market. Okay, variance is the risk, one of the measure. You see whether these 2 assets have the same risk or different risk. Okay, and especially when we don't have the good model for it, right? So for cryptocurrency, right? You don't have a good model, right? For the standard finance model for a stock, for the bond, you have a good valuation model. Okay, for new investment thing like cryptocurrency, okay, I don't think now we have a satisfactory modeling to say the changes of the price. Okay, for the trend, actually you can say demand and supply is a good way, but I mean during the day you see the changes. I mean it's hard to justify the thing changes during the day. In the day is hard to say. Okay, but that is something you want to see. Suppose you want to invest in certain cryptocurrency, which one to invest, right? And maybe you want to compare the risk. Okay, so that is something, the application there. I mean, there's a lot of applications you can check the book, but I cannot possibly go over. So all this basically we're doing that without knowing the variance. Okay, so basically you will see that what we're doing is no different from doing this here. Okay, everything is same as doing this. Okay, the only difference is when we compare the mean difference. Okay, is still we will also see the normal distribution. Okay, but the only difficult part is how to derive the variance. Okay, and what's the degree of freedom? Okay, so the difficult part is, let me highlight the difficult part here. Okay, you will see the similar thing. Okay, this guy is don't know what to do. Okay, and this guy is also you don't know what to do as well, and this guy. Okay, so basically for the 1 and 2, you see the same formula, but what is S was to be N here, was to be N minus 1 here. We will have some change in the formula, but everything same. Okay, and this one pair the population. Okay, will be very similar to this formula again. Okay, but just how to define all these 3 will be different. Okay, but there you will see we don't do the proof. Okay, we just give the formula. Okay, because we don't have time to go over the proof, but proof is in the handout already. If you really want to work it out, you can just look at it. But that's I don't want to do any proof. Okay, and let's go. Okay, let's go means we continue, not go away. Okay, so don't worry. As I said, this will be same, exactly the same, but different formula. Okay, so there should be no surprise. Okay, but there will be some I try to give you some explanation. Okay. So the first thing is, okay, we don't know the variance. Okay, but we hope that we can make some assumption to make it our life easier. Okay. The first thing is we make assumption that the two things we're comparing have the same variance, although we don't know. Okay. And why we can make that assumption? Maybe we think that the variance is the sample error should be similar. Okay. So for example, when is a good idea about this is look at, for example, you want to compare maybe general study. Okay. Or look at the GPA of male and female. Okay. Unless you have, I think it's good assumption, working assumption, until proven otherwise. I mean, the variance should be the same, right? Maybe you just want to say, I want to test the variance, the mean that they're different. Okay, and you want to say they have equal variance. Of course, the real answer should be whether they're equal variance or not. You should do the F test later. I mean, because whether equal variance, actually we have the idea, right? Because later we can compare. Okay, you should use this after you pass this test, usually. Okay, if you pass this one, you should do this. Okay, and in general, you should do this at the beginning, unless you have strong reason to believe that, say, male and female may be the same variance, but they have a different mean. Okay, if you can't make this assumption, you think this is, say, problematic, you should go to this one. Okay, so I hope I made myself clear. Just let me repeat. Okay, if you are happy to make some assumption saying that they have the same variance, okay, like male or female, maybe it's okay. Okay, but otherwise you should go for the second one. Okay, and you will see the first one make the life easier. Okay, second one, the life is a little more difficult, and that's why we teach both. Okay, otherwise why don't we teach the easier, the most general one, right? This is more general, this is a little bit more specific. Okay, this should only be used in general if this you can pass this test. Okay, but we don't talk about this until later stage. Okay, so let me repeat this one, right? Why we want to do this is want to see whether, say, male or female are the same, maybe same GPA or same income, okay, or same this, same that, same what, two group of object, right? Or you're gonna want to see whether the, as I said, the vaccine, right? Sinovac, BioNTech, BioNTech, do they have the same antibody? Okay, so that's the test. Okay, so how do you do the test? Okay, so actually, I mean, I try to describe the proof. Okay, but I'm not going to do the actual proof. Okay, X1 bar, the sample mean for a normal distribution, right? Central limit theorem. This guy also central limit theorem, right? Normal. And remember when we talk about topic 5, topic 3, right? Difference of normal. If they're independent, it's still normal, right? Sum of the normal is normal. The difference of normal is normal. It's only true for normal, okay? It doesn't true for anything. Only for normal is very interesting. The bell shape plus bell shape is a bell shape. Bell shape minus bell shape is also bell shape. Okay. So that means that the difference of this, okay, according to this minus this is also a bell. Okay, it's a mean zero bell. So same as this guy. Okay. There's nothing deep here. The only deep thing is here why we have this guy. Right, the variance. Okay, it's a complicated object. Okay, we are not trying to show you why this is true. Okay, but just this. Okay, you can show this is a good estimator for the variance of this guy. Okay, this is an error. This is the unbiased estimator. Okay, we don't explain why this is unbiased, but we just say this is the case. Okay, this is the formula. And you want to prove it's not that difficult, but we don't. Okay. I think we have the proof in the. If you want to look at the proof, I say, yeah. I think I do the proof here. I'll prove it Y. At the end, you get a T. But I'm not going to do any of those, because I'm pretty sure even though I talk about this, you forget. I mean, because we don't do exam on this and no one care. Okay. I mean, if you care, you can look at it and say, ask me. Okay. But just we have, I mean, you can see the same formula in the textbook. So we have belief. Okay. We have 95% confidence that this is true, right? So let's be actually 100% this is true to prove it, right? So there's no way this is wrong. So this is a SP as a pooled variance. We'll do in the next slide. Was this, but you 1 over n minus 1 over n plus it's very weird formula. Okay, I admit this is very weird. Okay, but this guy is a little bit easy to explain, right? N1 minus 1 plus N2 minus 1, okay, because each one is N1 minus 1, right? So you have two of them together, then just add together. Okay. So again, I don't explain. But one of the reason is because you estimate two mean, so that's why minus 2. But anyway, we don't want to go further why this is the case. Okay. Just take it for granted. Okay. N1, N2 minus 2, and this is the formula. Okay. What is this formula? Pooled variance. Looks like another crazy formula. Again, we're not going to prove anything of this. This is the formula. Okay, you just use it. Okay, and the proof is not difficult, but since we're not required to do math, you can just have a good belief on that. Okay, and the critical value will be just like this. Okay, and interval estimator, there's nothing, right? This is this plus minus this guy, right? The same thing here. The only difference is this guy is here, and this is the denominator, right? So you can see there's no secret of this, right? Everything actually from this on, this whole chapter always like this. Okay, I'm not going to prove every single thing here because you will see for the rest of our class, we'll give you a lot of formula we don't prove. Okay, but of course, the proof is already in the slide, but we don't go to the proof. But just from now on, you need to some memorization of what formula you're going to use, okay? Because we don't really prove it, okay? Let's at the end we go to the example, okay? To illustrate how this is being done, okay? I think that's the most important, how to use it. And of course, the calculation wise, it's just I think we just need it for demonstration, right? Because usually when you actually do it in practice, you don't actually go this kind of step. You just plug in the thing in the program, just come out the answer. Okay, either Excel or the R will give you the answer directly. Okay, but we need to know how it comes out about it. So let's go step by step how this formula comes in. Okay, so here we have two population. Okay, we assume that the same population variance. Okay, let me repeat it. How can you do this assumption? One is your boss tell you this is assumption, then you do it, right? The second is you believe that can be reasonable. It's reasonable. Say male and female may be a different meaning. You're willing to make this assumption. Okay. The third one is based on the F test. We do it later. Okay. Up there, maybe next class we'll be doing that. Okay. So now the first thing is the first sample, the sample mean of 40, sample variance of 4. Okay. And population, the other one have sample size of 40. So N2 is 40, X2 is 42, and S2 is 3. Okay. The question is try to see if they're the same. Okay. So remember, this is very commonly used formula. Okay. So what we're going to do is we calculate SP first. Okay. And then we go to the next slide and calculate T. Okay. And then do p-value and interval. Okay, that's low. So this is the roadmap. We do step by step. Okay. So the first thing is to calculate pool variance. What's pool variance? Go back to the slide here. Looks complicated, but it is not that complicated. Let's understand it. This is just a weighted average. Okay. Sample variance S1, sample variance S2. Okay. It's just a fraction. Okay. Is N1 minus 1 plus N2 minus 2 is fraction of this. This is a fraction of N2. Okay? Basically, just like weighted average between two variants. Okay, it's a weighted average. Okay, weighting for the variance one is N1 minus 1. Weighting for S2 squared is N2 minus 1. It's a weighted average between two variants. Okay, this is pull the variance. Okay, so let me go it again. Is N1 is 50, 50 minus 1, 40 minus 1, 50 minus 1, right? N1, N1, N2, right? With N2, N1, N2. S1, S2. S1 is 4, S2 is 3. Okay, so turn out to be 12.8. Okay, so this is in the middle of the two, right? Because 4 squared is 16, right? This S2 is 9. So it is actually between 16 and 9. Okay, which one is more reliable depends how big the size, right? Suppose this have larger sample size, right? So that's why it's closer to 16 than closer to 9. Okay, if you look at the formula, if N1 getting bigger and bigger and bigger, you're very close to 16. If N2 get bigger and bigger, you're close to 9. Okay, just 2N, 9 and 16, just see how many sample, right? Because the more sample you have, actually more reliable, right? So that's how you estimate the pool variance. Okay, once you pool variance, you can calculate the test statistic. How to get that? Let's go back to here. It's the formula. Okay, we have this 12 point something. Just put in 50, 40, right? And we say that the same is 0. Okay, just take a difference between the two mean. Okay. This mu1 and mu2 is 0. Okay. X bar is 40. X1 bar and X2 bar is 42. So it's 40 over 42. Okay, over that complicated guy. Okay, turn out to be negative 2.6. Okay, so what is so there are two things to do here. Okay, let's draw it here again to show you the logic. Okay, so as I said, they're the same thing here. So we have X bar 1 minus X bar 2, right? And under the null, they're the same. So we have a normal again. Okay, so that is the thing we have. Okay, so we know that actually we have the difference is 40 minus 42. Okay, so actually what we have is here. The data so is negative 2. Okay, so the question again is two-tailed test, right? So what we want is to ask if this area two-tailed multiplied by 2 is bigger than alpha. Okay, and of course you just convert this to this one, T. Oh, it's a black one. T 88. Okay, Y88 is N1 plus N2 minus 2. 50 plus 40 is 90 minus 2 is 88. Okay, so T88 here. And you want to ask the question. This is negative 2.625. Okay, I hope I do not need to go to Excel. This area multiplied by 2 or by 2. Okay, you can calculate this area. Is 0.1 is 1%. Okay, 1.2%. So you reject at 5%, but you can't reject 1% because it's 0.102. So you can reject 5%. You can reject 5%, reject 10%, but you can't reject 1%. Okay. Alternatively, you can use the T value. Okay, the critical value. Critical value. I think now we calculate. I'm going to repeat. It's 1.987. Again, this value is way beyond that, so you also reject. Okay. So lastly, I don't want to take more time. The last one is this one, interval. Okay, just put 40 minus 45. Right. Put now is this number. Remember, right? The critical value. This number put in here, right? And this is N1, N2, and this is pooling sample, SP square, right? This is N1, this is N2. Okay, so you can just calculate this number, and this gives you convolutional interval. Okay, so this gives the interval the difference. Okay, of course, in that also means that if this interval includes 0, then you can't reject the null, right? If it excludes 0, you can reject. Okay, so I don't want to take more time. It's 1 minute past the time, so I will see you on Wednesday. We'll be in the lab. Okay, as I repeat once more, whether we will be in the lab again on the Monday, whether here depends on whether we can finish on time, because typhoon killed us one class, so we have to all the time we have to move. Can have this class here on Monday, but let's see. Hopefully we can, but if we can't, we have one more class on Monday on the lab. Okay, so fun. See you. I will see you on Wednesday on the lab.